Hello everyone, welcome to the third tutorial of MTE241. Today in this tutorial I'm going to cover the questions inside the question sets 3 that is uploaded on the Learn. Let's get started. Question 1. The following code inserts a node at the end of the single linked list. Add acquire, add mutex and release mutex to make it a thread safe. So basically let's do a quick look over the code to see what exactly it does. So we have a function which is tail insert. Then what we do here is that we memory allocate a node, and then we take this node, like we assign the data to this node that is like one of the arguments of the this function or thread. Then we will assign null to the next of this node. If the list head is null, it means that the list is empty. We are going to make this node as a head of the linked list. Otherwise, we are going to make, we are going to change the tail of the linked list and then change the node pointer accordingly. So what does it mean to have a thread safe or reentrant thread? So basically, a thread safe code only manipulates the shared data structure in a manner such that it ensures that all threads have properly and fulfilled their design specification without unintended interactions. By the other words, we want to have, when we have like multiple threads working at the same time, we do not want to have any interruption or interference from other threads on the shared variables. So this means that a thread to be a thread safe. So what we need to do here is the most trivial approach to make this function to be thread safe is to use a mutex, as explained in the title of the question. So the easiest way is to acquire a mutex when we start or when we enter the function, and then release this mutex when we are done. This is the most trivial things that we can do to make this function thread safe. However, is it really an efficient work or efficient approach to do that? Does it make any performance degradation? Yes. How should we make this thread safe if it's not efficient? So what we can do here is that we need to go through the code and see what parts of the code are important for us, and we do not want to have any interruption or interference on those shared resources. So for example, let's say the first line, which is a memory allocation or a malloc. Is it really important to protect this line? No. Or how about the next two lines, node data equal to data, and also assigning the null to the next of the node? These are not basically the important part of the code, and there is no, the interference from the other cores cannot make any difference, because each thread will have its own arguments, and these are done at the arguments of the a single thread itself. So what we can do here is that we only acquire the mutex when we are going to touch or change or modify a shared variable. So in this case, what we can do here is that the first block is not much important. Basically, it's not the one of the interest of being interfered, but the second block, which starts from the if statement, is important because we are going to check or we are going to change some variables that affect basically the some of the shared variables across all the threads. So the better approach would be acquiring the mutex before the if statement and then release it after we are done with changing the tail of the linked list. Okay, so this ends the first question. Let's go for the next question. So the pseudocode of a non-reusable barrier is given as below. We have a terms of style equals to 0, mutex, count, and 7 lines of code. Complete the following table, just showing the task's execution of lines 4, 6, 7. Assume that tasks execute initially in a numerical order. Assume that the turnstile is a hypothetical blocking semaphore from lecture that has negative value when tasks are blocked, and that blocked tasks unblock in the first in first out order. When task A unblocks task B, assume that task A continues executing until it blocks. Okay, let's go forward. This is the initial state of these three tasks. So basically we have task 1, 2, and 3. All of them are in a state of ready. Then we have a turnstile. At the beginning of the this process, the turnstile is equal to 0. And note that the n inside the code at the right, inside the source code, represent the number of tasks. So in this case, we have 3 tasks. So the n is equal to 3. Okay, let's start with the first action. So the first action is that task 1 is going to, as you can see in the source code, it goes to the line 2, it takes the mutex, it increases the count, so the count will be 1. The count is not equal to 3, so it's not going to signal anyone. Then the mutex will be released. Then it goes to the wait turnstile. So the wait turnstile, what it does is it decrements the turnstile by 1, right? So the turnstile value would be -1 in this case, and the state would be blocked. The next line, basically task 2 does the same thing. So it goes to the part of the code, then it acquires the mutex, then it increases the count. The count will be 2 in this case. 2 is not equal to 3, so it's not going to signal the turnstile. It releases the mutex, then it waits for the turnstile. So again, the turnstile will be decremented by 1. So the turnstile, new turnstile will be -2. The state will be blocked. Task 3 goes to the function, to the thread, and it acquires the mutex. It increases the count. The count will be 3. So now the count is equal to the n, which is 3 in this case. It signals the turnstile. So the turnstile will be incremented by 1. From -2, it goes to the -1. The tasks are going to be unblocked by a first in first out order. So the first task that was blocked was task 1. So the state of the task 1 will be changed from blocked to ready. Then it goes to the wait turnstile at line 6 in the source code. Again, the wait turnstile will decrement the turnstile by 1. So the new value of the turnstile would be -2 in line here. So the action would be wait. It unblocked the task 1, and it himself goes to be blocked with the turnstile of -2. So basically in this case, -2 means that there are 2 tasks that are blocked at this point in time. Okay, so task 1 was ready, became ready at the previous action, right? So now from line 6, it goes to line 7. It gives the signal. So the signal turnstile will be incremented turnstile 1 by 1. So the new value of the turnstile would be -1. The other task would be unblocked by the first in first out order. The task that was blocked earlier was task 2. So the state of the task 2 will be changed to ready. Then we have the signal at line 7 in the code for task 2. Again, it increases turnstile. The turnstile would be 0, and the task 3, which is the last task that is blocked, will be unblocked, and it gives the signal at line 7 here. So the final number or the final value of the turnstile would be -1. So please note that we start with an initial state, right? So initial state of this task 1, 2, and 3 were that all of them were ready and the turnstile was 0. Now let's look at what happened right now after like going through this code and releasing everything. So again, these task 1, task 2, and task 3 are ready. However, the turnstile is not 0 anymore. So the turnstile is 1. So the behavior of the code or the behavior of the turnstile and the semaphore will be changed, will change basically compared to the case that we just analyzed, right? So this case represent basically represent the non-reusable barrier, right? So in question 3, it says that fix the barrier pseudocode to make it reusable. So in the previous question, we saw that the barrier code that we have described was not reusable because the state at the end was not the same as the state at when we started, right? So do this by adding a second ternstile. So as a hint, it says that we are able to add another ternstile. As task exists the barrier, they should decrement the count, and the last task through should decrement the query. The first ternstile to prevent task from reusing the barrier without blocking. So the answer is given in the question, right? So what we need another block of the ternstile, another block of the code, similar to what we had in the previous non-reusable ternstile code. However, in this case, we are going to use two ternstile. Ternstile 1 initialized with 0 and ternstile 2 initialized by 1. So in this case, whenever the count is equal to n, we do the same thing. So what we do is that we signal the ternstile 1, but on the other hand, we wait on ternstile 2. In the second part of the code, we have the same thing, but in other way, right? So it means that just assume that we are in the last state of the question 2. For example, we are in this line where the signal came from task 3 and ternstile is 1, right? So now assume that we are at the second part of this code, which is the reusable barrier. In this case, it decrements the count. So the count in this case will be decremented. Then if the count is 0, this is the last part, like corresponded to the last section of this question 2 answer. So if the count is 0, what it does is waits on the ternstile 1. So if we go back here, the ternstile was 1. So if we wait on the ternstile 1 with another ternstile, what it does is that it decrements the ternstile 1. So the ternstile 1 would be 0. So this part of the code does not affect the behavior of the barrier implementation. However, it reverts or restore the state of the the ternstile, the state of the code, the counters and everything, etc. Basically the same as it was at the beginning when we started, right? Okay, so let's go for the next question. So it's kind of the comprehensive question, which is very important. So suppose that we have a singly lane bridge, and once people start passing over it, when people start passing over in one direction, others can continue crossing in that same direction until the last person traveling in that direction gets off the bridge. Then, if there is someone waiting to go in the opposite direction, they would then start traveling across the bridge. Fill in the code below as indicated to implement this scenario. Okay, let's talk about this case. So what we need, basically this is provided by question. It says that we need to first declare the bridge variables. What we need, what attributes this bridge has. The next one is initializing these variables. So whenever we have some variables, no matter what, we need to initialize these variables, right, with some numbers. Then we have get onto the bridge and get off the bridge. As indicated by the question, the cars that are going in one direction to the bridge will block the other cars that wants to go to the opposite side of the bridge from the other way, right? So we need to implement get onto the bridge function and get off the bridge function. So it's kind of clear and obvious that we need to use a mutex, right? We need to protect somehow the cars that are going in one direction from the other ones. Okay, let's start with basically the bridge, declaring the bridge variables. So what do we need here? So basically a bridge. So the first important thing is the direction, right? We want to have a direction attribute to this bridge at any point in time, because we want to know which direction is allowed at a specific time. So we need a variable which is direction. Different tasks can change the direction and look at it, right? So we need to protect the direction variable with a mutex. So what we do not, the last thing that we want is to basically change the mutex every time somebody enters a breach, right? We need to protect that. It is not possible that basically everyone could possibly change the direction. We need a variable to track how many cars are currently crossing, and we need to keep track of how many cars to wake up, meaning that if some cars are crossing the bridge, some of the cars that wants to go in the opposite of the side, opposite direction of the bridge, they need to be asleep, right? So we need to wake them up. The other thing is that we need to put any cars that can't cross to sleep and wake them when they can cross. We need a semaphore for that, for sure, because the semaphore is a protective variable or function that lets us know how many. I mean, the count. It has the count capability that lets us know how many we need to wake up or how many we need to put to wait, right? Okay, so the first thing is direction bridge. We call it bridge direction. And then, and also dir_t is a type defined enumerate. If you can, look at the above of the code, we have north equal to 0, south equal to 1. It defined as a dir_t. And then we have a mutex bridge, we have a mutex called bridge mutex. And then we have a waiting count, crossing count, and also we have a semaphore, which is waiting semaphore. So we are only going to signal the semaphore when we want to go to sleep, right? So initialized semaphore should be, the semaphore should be initialized to 0. We initially don't care which direction the bridge is configured initially, because if somebody exists, it goes to that direction. If nobody exists for that direction, the direction will be changed because there is no crossing for that specific direction. We start with no cars waiting or crossing because, I mean, it's a initial value or initializing the bridge variables, so it doesn't matter, right? So the OS mutex, so we have the mutex for bridge mutex, then we have the direction, we arbitrarily choose to make it to be north. Then we have a semaphore for waiting. In this semaphore will be initialized with 0 as explained. Waiting count and crossing count will be 0, and they will be changed according to the threads and what they does, right? Okay. The next part would be get onto the bridge. So what should we do here, really? Basically, if we are going in a correct direction, we should increment the crossing count before crossing, right? And if you're going in a wrong direction, but there is no one crossing, we change the direction and increment the crossing count before crossing. If you are going to in the wrong direction or in the opposite direction, and there is someone crossing, we register that thread or that car and go to sleep. Basically, we need to put to wait until basically everyone that crossing are done. Then we change the direction and then we go, right? Okay, so the first thing that we want to do is that we want to define, or we want to know that what is the direction and what should be the direction. So first we take the mutex for that bridge, for that bridge mutex. Then we check if the bridge direction is equal to the my direction. My direction is for each car that wants to cross the bridge, right? So if this is equal, it means that I am allowed to enter the bridge. So basically what I do is that I will increment the crossing count and then I release the mutex. Else if the crossing count is 0, it means that the direction is not equal to my direction and the crossing count is 0. Again, now I can detect the mutex, what I do, and then as I did before, and then change the direction. So my direction will be associated to bridge direction. I will increment the crossing count and then release. The other way around, it means that the bridge direction is not my direction and also the crossing count is not 0. So it means that I need to go to wait, right? So the waiting count will be incremented I release the mutex, and then I acquire a semaphore to indicate how many are basically waiting, right? The last part would be get off the bridge. If you're the last car in our direction and there are cars waiting, we change the direction and wake up all of the waiting cars. And for sure, the number of cars crossing is now equal to the number of cars previously waiting. So it's obvious, I guess. What we do here is that we take the mutex, then we decrement the crossing count. So if the crossing count is equal to 0, we are going to wake up everyone that was waiting beforehand. So to the number of, like, we have this number from the semaphore, and we loop over until we release everyone in a waiting cycle or waiting counts. Then we specify the direction based on the being north, being south, and so on and so forth. And basically the crossing count now would be the waiting count, and the waiting count, the new waiting count, would be 0 because everyone that was waiting, they are now allowed to basically cross the border, cross the bridge. Okay, that was it for question 4. Let's go for question 5. Okay. In the following is a solution to the writer's problem. So in the left, we have a writer task. In the right, we have a reader task. So the writer task, whenever it wants to perform an operation, it takes the mutex on the not busy, then it does the writing, and then it releases, right? However, in the reader tasks, we could have multiple tasks reading at the same time, right? So what it does is that it takes the mutex, it increments the readers. If the readers is equal to 1, it means that it can basically acquire the semaphore, and then the mutex will be released, perform reading. Then we have acquire mutex and then we decrement the reader when we are done. If the reader is 0, it means that we can basically release a semaphore on the not busy and then let writer task goes, right? So we want to know that if we could have concurrent readers. Actually, based on the code that is provided, it's possible that to have multiple concurrent readers, right? Because there is nothing in the code for the reader tasks that prevent us from having 2 readers at the same time. It's only the fact that basically perform reading, right? Do we have exclusive writers? For sure, because the reason that we have OS mutex acquired on not busy is that we are going to have exclusive writers, because when a writer task is performing writing, no reader task can go ahead, because there is a mutex on that to protect this basically variable, right? And is there any facility to prevent no starvation? I believe no, right? Because if you look at the reader task, it goes and goes. Basically, it increments the readers until the readers is not 0. It does not allow the writer task to go ahead and go through, right? So as long as the reader task exists and wants to do the reading process, it does not allow the writer task to go ahead and do whatever it wants to do. So what we do here in this case, we say that there is no facility to basically prevent no starvation. Okay, so that was it for the third question sets. Please let me know if you have any question. You can post it online on Piazza, or send me an email. I will try to answer it as fast as possible. Thank you so much for watching this video. I hope you have a great rest of the term.